It's funny. We navigate this incredibly chaotic world every single day, right? You open your weather app and it says there's a 30% chance of rain.
Right.
Or your email mysteriously filters out a spam message before you even see it. Or, your phone magically tags all the photos of your dog, completely ignoring the photos of your cat.
Yeah, that's a classic example.
And usually we just accept it. We treat it like it's either pure magic or just total unpredictable chaos.
Well, I mean, it is entirely natural to feel that way. Our brains, they naturally crave absolute certainty.
Totally.
We want things to be a sure bet, to be completely predictable. But the reality is almost everything around us operates in this invisible humming landscape of randomness.
But what if I told you there's a hidden mathematical architecture behind all of it? Welcome to today's deep dive. We're extracting the blueprint from Chapter 3, which is all about probability, in the Open Intro Statistics textbook.
It's a great chapter.
It really is. And for you listening, our mission today is to completely demystify probability. We aren't going to sit here and make you memorize dry formulas or sound like a boring math lecture.
No, definitely not.
Think of this deep dive as your shortcut to understanding the hidden laws that govern everyday randomness.
Exactly, because mastering these concepts, it isn't just for passing a test. It is an absolutely essential tool for critical thinking.
Yeah.
We live in a world that is completely overflowing with data, and while algorithms are constantly making decisions for us in the background.
All the time.
Right, and if you don't understand the rules of probability, you can't possibly understand how those decisions are being made.
Okay, let's unpack this. Before we can start calculating the odds of complex, real-world events, the source material suggests we first need to agree on what the word random actually means.
Yes, defining our term.
Yeah, and this threw me for a loop initially, because doesn't everyone know what random means? I mean, it means unpredictable, right? But in statistics, the definition is completely different, isn't it?
It is very different. In statistics, the probability of an outcome isn't just a guess. It is literally defined as the proportion of times that specific outcome would occur if we observed a random process an infinite number of times.
What? Infinite.
Infinite, it's always a value between 0 and 1, or, if you prefer percentages, between 0% and 100%. But the crucial concept there is that idea of infinite observations.
Got it.
We are using probability to build tools that describe apparent randomness over the long haul.
Over the long haul. Okay, the textbook has this amazing visual simulation to illustrate this, and I want to paint the picture for you listening. Imagine a computer simulating a roll of a standard six-sided die, but it rolls it like 100,000 times.
Which is a lot of rolls.
Yeah. Now, we all know the chance of rolling a 1 is 1 in 6.
Which is roughly 16.7%.
Right. But if you look at a graph of this simulation in the early stages, say, just the first 10 or 20 rolls, the line representing the proportion of ones is violently jagged.
It's all over the place.
Exactly. It's swinging wildly up and down. At roll 10, you might have 0 ones, or you might have 5. It looks completely chaotic.
And if you stop there, it appears to completely defy the mathematical rules. But what you are looking at is the essence of the law of large numbers.
Yep.
The law basically states that as more observations are collected, the proportion of those occurrences eventually converges to the true probability.
So it's smoothed out.
Exactly.
Yeah.
Fast forward to 10,000 or 100,000 rolls on that graph, and that violently jagged line flattens out perfectly. It becomes a perfectly straight horizontal line at exactly 1 in 6. The chaos stabilizes.
It is so satisfying to think about. But I want to push back on this fundamental idea of randomness for a second.
Oh, go for it.
Because there's a fascinating footnote in the text that really caught my eye. The author suggests that even a roommate's behavior could be modeled as a random process.
Yes. The messy roommate.
Right. Now, my old college roommate leaving his unwashed dishes in the sink didn't feel random at all. I mean, it felt like a deeply intentional choice to annoy me.
I'm sure it did.
So, is anything truly random, or is random just a word we use for things that are simply too complicated for us to predict exactly?
Well, if we connect this to the bigger picture, that is the exact right question to ask. Whether a process is perfectly fundamentally random at some microscopic quantum level.
Like physics stuff.
Yeah, exactly. Whether it's that or whether it is just highly complex and influenced by a million tiny variables we can't possibly see, like your roommate's mood, their class schedule, how tired they are, what they ate for lunch.
Right.
It doesn't actually matter for the math. Modeling that behavior as a random process gives us a highly reliable mathematical framework to make predictions.
So I don't need to know every single variable in my roommate's life.
Exactly. You don't need perfect knowledge of the universe to predict the likelihood of an outcome. Over the course of an entire semester, if you track the sink, you might find a, say, 30% probability of dishes being left there.
Okay.
As long as you have the law of large numbers on your side, you can model the complexity.
That makes a lot of sense. It kind of takes the pressure off needing to be omniscient. So we know how to measure a single event over time, but life rarely throws just one isolated event at us. Usually we are dealing with multiple possibilities all happening at once.
Which is where things get interesting. When multiple things can happen, we first have to figure out if we are dealing with disjoint outcomes.
Disjoint.
Yeah. You'll also hear them called mutually exclusive outcomes. These are two outcomes that absolutely cannot both happen at the exact same time.
Like what?
Well, the classic simple example is if you roll a single die, you can roll a 1 or you can roll a 2. It is physically impossible to roll a 1 and a 2 on the exact same single die.
Right, because there's only one top face.
Yeah.
And when events are completely disjoint like that, calculating the probability is super straightforward. You just use the addition rule. You literally just add them up.
Yep, that's simple.
So the probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6. So the probability of rolling a 1 OR2 is simply 1/6 plus 1/6. 2/6. Easy.
Very easy.
But here is where the real world complicates things. I was looking at the text example of a standard 52-card deck, and my brain completely short-circuited.
The playing card example is a perfect way to show how our intuition fails us.
Exactly. Let's say I want to find the probability of drawing a diamond or drawing a face card, a jack, queen, or king.
Right.
Now, I know there are 13 diamonds in a deck, and I know there are 12 face cards in a deck. My brain immediately just wants to add those two numbers together. 13 plus 12 is 25.
Makes intuitive sense.
So 25 out of 52 cards. But the source material loudly warns that this is completely wrong. Why does that simple addition fail here?
Because the events are not disjoint. They can overlap. By simply adding 13 and 12, you've fallen headfirst into what we call the double counting trap.
As I was reading that, I came up with an analogy to try and cement this in my mind.
Let's hear it.
Imagine you're at a party, and you're trying to count how many of your friends are wearing glasses and how many are wearing hats.
Okay, hats and glasses.
You walk around the room and count 5 friends with glasses. Then you count 4 friends with hats. If you just say, well, 5 plus 4 is 9, you're going to get the total number wrong.
Because of the overlap.
Right, because you didn't realize you just accidentally double-counted the hipster in the corner wearing both a beanie and thick-rimmed spectacles. You counted him once for the glasses group, and then you counted him a second time for the hat group.
That is a phenomenal analogy, and it perfectly illustrates the mechanism behind the general addition rule.
The general addition rule.
Yeah. When events can overlap, you take the probability of the first event, add it to the probability of the second event, but then you absolutely must subtract the probability of both happening at the same time.
To fix the double count.
Exactly. You had to subtract that intersection so you don't count the hipster twice.
Okay, so if we take that back to the deck of cards, 13 diamonds plus 12 face cards, but then we have to look for the overlap.
The cards that are both diamonds and D face cards.
Right, which would be the jack, queen, and king of diamonds. There are 3 of them. So 13 plus 12 is 25. But then we subtract those 3 overlapping cards so they aren't double counted. We end up with 22.
Spot on.
So the real probability is 22 out of 52.
Exactly. And I want to pause on your hipster analogy for a second because that simple double counting trap is one of the most common fundamental errors people make when assessing risk or reading data in the real world.
Really?
Oh, absolutely. We constantly see 2 alarming statistics in the news, add them together in our heads, and panic, completely forgetting that those 2 groups of people or events heavily overlap.
Wow, it artificially inflates our perception of reality. It makes problems look way bigger than they actually are.
It does.
So how do professional data scientists completely avoid that double counting trap when they are looking at complex systems?
Well, they map everything out. They use something called probability distributions. A probability distribution is essentially a master list of all possible disjoint outcomes for a given scenario. But to be mathematically valid, this master list has to follow three very strict rules.
Right. The text lays these out clearly.
First, all the outcomes listed must be disjoint. Going back to your party, no hipsters wearing both hats and glasses are allowed in the main categories. You have to create a brand new, separate category just for them.
Got it. No overlaps.
Second, each individual probability on the list must be a valid number between 0 and 1. And third, and probably most importantly, if you add up all the probabilities on the list, they must total exactly 1.
Meaning 100% of the possibilities are accounted for.
Precisely.
The source material shows a really illuminating example using U.S. household incomes to prove why these rules matter.
Yeah, the three tables.
Right. It presents three proposed distribution tables for income brackets, but only one is mathematically possible. One of the fake tables actually includes a negative probability.
Which is impossible.
Right. It suggests a negative 27% chance of making a certain income, which obviously violates Rule 2.
Yeah.
You can't have negative odds.
No, you cannot.
And then another table adds up to 109%, which violates Rule 3. Everything must sum to exactly 100%.
And knowing that everything must sum to exactly 1 is what unlocks one of the most powerful analytical tools in a statistician's toolkit.
Which is?
The complement of an event.
Oh. Here's where it gets really interesting. Let's talk about this complement hack because this completely blew my mind.
It's a great trick.
The complement of an event, let's just call our event A, is simply all the possible outcomes that are not in event A.
Right.
And because we just established that all possible disjoint outcomes must add up to a total of 1, the probability of event A happening plus the probability of it not happening always equals 1.
Exactly.
Which means if you want to find the probability of A, you can simply take the number 1 and subtract the probability of its complement.
It sounds a bit like abstract algebra when you say it out loud, but in practice, it is a massive real-world time saver.
It really is. Let's walk through a scenario from the text for you listening. Imagine you and I are playing a board game. And to win, you need to figure out the probability of rolling a sum less than 12 using 2 standard 6-sided dice.
Okay.
Now think about how annoying that would be to calculate the hard way. You would have to painstakingly calculate the odds of rolling a 2, which has its own combinations.
Uh-huh.
And then you add that to the odds of rolling a 3, and then a 4 and a 5, all the way up to 11. That is 10 separate complex calculations. You'd be there for 5 minutes just crunching numbers.
Or you could just find the complement. You ask yourself, what is the one outcome that is not less than 12?
Rolling exactly a 12.
Right. And calculating the odds of rolling a 12 is incredibly easy.
Mm.
Just one combination, a 6 on the first die and a 6 on the second die.
Out of 36 total combinations.
Exactly. That's a 1 in 36 chance.
So instead of doing 10 calculations, you just take the total universe of possibilities, which is 1, and subtract that 1 in 36 chance.
Which leaves you with
1 minus 1/36 leaves you with 35/36. Boom. You get the exact same answer in 2 seconds. It's brilliant.
And thinking backward like this, looking for the complement, it isn't just a clever math trick for board games. It's a really powerful critical thinking framework.
How so?
Well, in business or science or everyday decision making, sometimes it is vastly easier to figure out the odds of something not happening than the odds of it happening. It completely reframes how you approach a problem.
I love that. Okay, so we've mapped out events that overlap, we've looked at these master lists of total distributions, and we've used complements to save time. But what about events that literally have no impact on each other whatsoever? Do they have their own rules?
They do. Then we are talking about statistical independence. Two random processes are independent if knowing the outcome of one provides absolutely no useful information about the outcome of the other.
Okay, give me an example.
Well, for example, the prices of different tech stocks usually move up and down together based on broader market trends, right? So they are not independent.
Right, they influence each other.
But flipping a coin and then rolling a die, those are completely independent. The coin does not care what the die does. There is no invisible gravity pulling them together.
And when events are truly independent, the text says we use the multiplication rule. You just multiply their individual probabilities together.
Exactly.
So if you roll 3 independent dice, say a red one, a white one, and a blue one, and you want to know the probability of getting At 1 on all three. You just multiply 1/6 times 1/6 times 1/6.
Which gives you...
You get 1 in 216.
Exactly. And that multiplication rule scales up to any number of independent events. The text actually uses handedness as a great human example.
Oh, right, the left-handed example.
Yeah. Let's say about 9% of the population is left-handed. That means the remaining 91% are right-handed.
Okay.
If you select 5 people entirely at random, what is the probability that all 5 of them are right-handed? You just multiply 91% by itself 5 times in a row. It comes out to about 62%.
But I have a major question about the textbook's methodology here. I'm going to push back on this scenario.
Go for it.
The text basically says that because selecting 5 people is such a tiny sample size relative to the entire population, it's safe to just assume these people are perfectly independent.
Right.
But is that actually safe? What if I randomly select my 5 people, but I happen to do it while standing inside a left-handers convention? I mean, the math of the multiplication rule would confidently tell me the odds of getting all right-handed people is 62%, but my actual reality standing in that room would be 0%.
What's fascinating here is you've just hit on the exact boundary where pristine theoretical math collides with messy real-world data collection.
Right.
Mathematical independence in textbooks often relies on the assumption of a perfectly random, perfectly pristine sample. In real life, context is absolutely everything.
Right, because my environment wasn't independent.
Exactly. If your sampling method has an invisible structural issue, like polling people at a specific convention or surveying a specific neighborhood or scraping data from just one specific social media platform, the sample isn't perfectly random anymore.
It's biased.
Yes. And if it's not random, that core assumption of independence completely falls apart. Your multiplication rule math will be totally flawless, and your final conclusion will be completely, dangerously wrong.
Which naturally sets up our final topic. Because the truth is, pristine statistical independence is actually quite rare. In the real world, variables are usually deeply entangled. Knowing one piece of information does change the odds of the next thing happening.
It does. And that brings us to the domain of conditional probability.
Conditional probability.
This is when we assess the probability of an outcome given that another event has already occurred or given that we have some piece of prior information.
To explain this, the textbook uses this incredible real-world data set called PhotoClassify. And this is where things get really practical.
Very practical.
It's an evaluation of a machine learning algorithm, an ML system, that is trying to predict if a photo uploaded to a website is about fashion or not fashion.
Right.
They have roughly 1,800 photos. The machine learning algorithm looks at them and categorizes them. But crucially, they also have a team of human beings carefully categorizing those same photos to act as the ultimate source of truth.
And looking at how the machine performed against the humans perfectly illustrates the profound difference between marginal probabilities and joint probabilities.
Okay, stop right there. If you are listening to this while cooking dinner or driving your car, your eyes might be glazing over at terms like marginal and joint probability. What do those terms actually mean in plain English for this photo classifier?
Fair enough. Let's simplify it. The marginal probability is based on just one single variable. It's the algorithm's solo guess, completely ignoring the human truth. So out of all 1,800 photos, the ML algorithm looked at them and declared, I think about 12% of these are fashion. That 12% is your marginal probability. It's just the machine talking.
Okay. And joint probability.
Joint probability looks at 2 or more variables overlapping. It's the intersection. So out of all 1,800 photos, how many times did the ML algorithm predict fashion? And the human truth agreed it was fashion.
The overlap.
Yes. That overlap only happened about 11% of the time.
Got it. So marginal is the solo guess, joint is the confirmed overlap. But the conditional twist is where my mind was totally blown. Because we don't just want to know overall percentages. We want to know how reliable this algorithm actually is under different specific conditions.
Exactly.
The text points out that if a photo is actually fashion, according to the humans, the algorithm got it and got it right about 64% of the time. Not amazing, but okay. BUT. What if the algorithm looks at a photo and confidently predicts not fashion?
This is where we find the critical blind spot in the technology. The algorithm predicted not fashion for the vast majority of the photos, over 1,600 of them.
Right.
But when you look at the human truth for just those specific 1,600 photos, you find that over 100 of them actually were fashion.
Wow. So given the condition that the machine learning algorithm confidently told you this is definitely not fashion, it was still wrong roughly 7% of the time. It missed over 100 photos.
It did.
So what does this all mean? For you listening, this translates directly to your everyday life. When a tech algorithm curates your social media feed, or a spam filter confidently labels an important work email as junk, the conditional probability of it being right is almost never 100%.
Never.
The massive danger is that we blindly trust the marginal prediction, the algorithm's confident little label, without ever stopping to look at the joint reality of its actual failure rate.
This raises an important question about how we evaluate the technology that increasingly runs our lives. The pure math explicitly proves that even a highly confident machine learning system has a distinct, measurable error rate when you condition its data against reality. Whenever an algorithm or a statistician or a news headline gives you a bold percentage, I highly encourage you to always ask, probability given what prior information? The condition completely changes the outcome.
That is such a powerful takeaway. Ask about the underlying condition. All right, let's briefly recap our journey today. We started by looking at how the law of large numbers brings mathematical order to chaotic things like single coin flips and die rolls.
We did.
We exposed the hipster double counting trap that totally skews how we view overlapping events in the real world. We learned how to use the complement hack to save time and think backward, and we exposed how the assumption of pristine independence can completely ruin a sample if you aren't careful.
What a lot of ground covered.
And finally, we used those exact same foundational rules of probability to evaluate the hidden blind spots of modern machine learning algorithms.
It really highlights how these theoretical concepts from a statistics textbook aren't just for academics. They are the exact same gears turning inside the technology we use every single day.
But I want to leave you listening with one final, slightly provocative thought to mull over, building on that last machine learning data set we just looked at.
Yeah.
Today, we looked at an algorithm being checked against a human source of truth. But what happens when that human source of truth is just fundamentally statistically flawed?
The data itself is noisy.
Exactly. What if the humans categorizing those fashion photos were tired, or inconsistent, or just bad at their jobs? If an algorithm simply learns and multiplies conditional probabilities based on noisy, flawed human data, are we just using the pristine, objective math of probability to quietly scale up our own measurement errors?
That's a scary thought.
Think about that the next time a computer confidently tells you what the odds are.
A pristine mathematical mirror reflecting our own noisy data.
Precisely. Thank you for joining us on this deep dive. The next time you open your weather app, or wonder how your phone categorized your photos, remember, it's not magic and it's not chaos. It's just probability. Keep questioning the numbers around you.